two 2-litre containers of gas are separated by a pipe, and the left container has 12 grams of helium with the following molar mass, and the right container has 22 grams of carbon dioxide with the following molar mass. And the stopcock is initially closed. Now, assuming ideal gas behavior and a constant temperature, while ignoring the volume of the pipe, which gas exerts the highest pressure on the container? Well, given the ideal gas law, and the volume of each container is the same, while the temperature is constant, then the pressure is proportional to the number of moles of gas. And you can find the number of moles of each gas by dividing the mass with the molar mass, and therefore the gas with the higher number of moles exerts the higher pressure. Now part B asks, if the stopcock is opened, find the total pressure exerted by the mixture of gases. Well, the total pressure, by Dalton's law, is equal to the sum of the pressures exerted by each individual gas. And you can find the individual pressures using the ideal gas law applied to each gas, with the following universal gas constant, and the temperature is given in degrees Celsius, which is 303 Kelvin, and you have the number of moles of each gas from part A, and the volume of gas is going to be 4 litres, with the stopcock removed. And part C asks to identify the gas with the strongest intermolecular forces. Well, the CO2 gas molecules are non-polar, so therefore the intermolecular forces between them are going to be London dispersion forces. And you're going to have the same interactions between the helium atoms, but the CO2 molecule is larger and is therefore more polarizable, so that's going to have a stronger interaction between its molecules. A mixture of helium and argon gas is confined in a 1 litre container at a temperature of 250 Kelvin. Now, if the total pressure is 3 atmospheres and the partial pressure of argon gas is 1520 millimeters of mercury, determine the pressure of helium in atmospheres. Well, using Dalton's law, the total pressure is the sum of the partial pressures of each component of gas. And 1 atmosphere is 760 millimeters of mercury. So we're given the total pressure and the partial pressure of argon in millimeters of mercury, which you can convert to atmospheres, and solve for the partial pressure of helium. Now find the number of moles of both gases. So we can do that by applying the ideal gas law to each individual gas. So we have the volume of the container, we have the temperature, and the ideal gas constant, and the partial pressure of each gas from part A. So therefore you can solve for the number of moles of each gas. And if the volume is increased to 2 litres, what's the new pressure of argon gas? Well, in this case, using the ideal gas law, where the temperature and number of moles of the gas is constant, so therefore the pressure by the volume is constant, and between the two states we can write the following expression. So given the partial pressure of argon gas from part A, and the initial volume of the container, and the new volume, we can solve for the new pressure.